All right, let's talk about memory. Have you ever wondered what a memory actually looks like? I don't mean in your mind's eye, but as a real physical thing inside your brain. Well, today we're going to dive into the amazing world of neuropsychology to see how scientists can literally watch our thoughts as they happen. So let's kick off with a huge question. Can you actually find a memory? I mean, is the memory of your first day at school stored in one specific spot, like a file in a filing cabinet? Or is it way more complicated than that? That's exactly what we're here to figure out.
So here's how we're going to break it all down. First up, we'll look at the big idea that makes all of this possible, a sort of map of the mind. Then we'll open up the psychologist's toolkit to check out the incredible tech they use. After that, we'll see that tech in action in a famous study, before looking at how it's used in the real world. And we'll finish up with a revision guide to make sure you've got all this locked in.
Okay, let's get right into it. The first concept we need to get our heads around is this idea that the brain isn't just one big gray blob. It's more like a map, you know? A map with different countries, each with its own special job to do. And this big idea has a name: localization of function. All it really means is that specific bits of your brain do specific things. So the part that handles what you see is totally different from the part that understands language. And that's different again from the part that stores memories. You can think of cognitive neuropsychologists as detectives, trying to figure out which brain area does what. That's a great theory, right? But how do we actually prove it? I mean, how do we peek inside a living brain to see what's going on? Well, for that, you need some seriously clever kit. So let's open up the psychologist's toolkit. First up, we've got the CT scan. The best way to think about a CT scan is to imagine a loaf of sliced bread. The scanner uses X-rays to take a picture of every single slice of the brain, and then a computer stacks them all together to build a really detailed 3D model of the brain's structure.
Now, for psychologists, this is a bit of a trade-off. CT scans are brilliant for spotting physical things, right? Like a tumor or damage from a head injury. But, and this is a really big but, it's a still photograph. It gives you a perfect picture of the brain's anatomy, but it tells you absolutely nothing about what the brain is actually doing.
So let's move on to our next tool, the PET scan. And this is where it starts to feel a bit like science fiction. Instead of just seeing the brain's structure, a PET scan actually lets us see the brain in action. It does this by following a tiny, harmless radioactive tracer as it zips around the bloodstream.
The way this works is just incredible, really. The tracer is designed to go where the party is. When a part of your brain is working hard, it needs more blood, so the tracer naturally gathers there. As the tracer breaks down, it sends out these tiny signals called gamma rays, which this huge scanner can detect. A computer then turns all those signals into a vibrant, colorful map of what your brain is up to.
Now, PET scans are super powerful because they show us which bits of the brain are firing up when we do something. But for psychology research, they have some pretty big downsides. They're expensive, they involve a little bit of radiation, and honestly, they've mostly been replaced by our next tool. And that brings us to the king of modern cognitive neuroscience, the fMRI scan. Now, an fMRI doesn't use any radiation at all. Instead, it uses incredibly powerful magnets to see where oxygen is in the blood. And the logic is really simple. When a part of your brain gets busy, it demands more oxygen. The fMRI is just brilliant at spotting where that oxygen-rich blood is rushing to. So, the reason fMRI is the go-to tool for researchers is pretty clear. You get a sharp, moving picture of brain activity with zero radiation. You can literally have someone in a scanner reading a book or looking at faces and watch which parts of their brain light up in almost real time. It's not perfect, mind you. Some of the early research had reliability issues, but the methods used today are getting better and better.
Okay, we've met the tools. Now let's see one of them in action. We're going to travel back to 1989 to look at a landmark study by a psychologist named Tulving. He used a PET scan to literally try and find where different kinds of memories live inside our brains.
First, we need to get clear on the two types of long-term memory that Tulving was looking for. Episodic memory is your personal highlight reel, the episodes of your life. And semantic memory is like your own personal Wikipedia, just facts and general knowledge that you know. Tulving's big question was, are these two types stored in different places? So here's how he did it. Just 6 volunteers lay inside a PET scanner. He asked them to think about either a personal memory, like a childhood holiday, or a factual memory, like the capital of a country. While they were thinking, a radioactive gold tracer was injected, and the scanner got to work, measuring where the blood was flowing in their brain. And this is where it gets really exciting. The results were crystal clear. When people were remembering personal episodic memories, the blood flow shot up right at the front of their brain. But when they were thinking about facts, semantic memories, it was the back of their brain that lit up. The conclusion was massive. Different types of memory really are physically stored in different locations. It was localization of function in action.
Right, exam hats on for a second. The key things to remember are this. It was a truly pioneering study that gave us scientific, objective proof of memory localization. You couldn't argue with the data. But, and it's a huge but, the sample size was tiny. Only 6 people took part, and the results were only really clear in 3 of them. That makes it really hard to say for sure that this is how everyone's brain works.
So, we've seen the theory and the tools in the lab. But this tech isn't just for academic research. It's used every single day to save lives. So let's see how these scanners go from the university to the hospital. A massive real-world application is in diagnosing a stroke. That's when the blood supply to part of the brain gets cut off. It's a huge medical emergency, and the FAST acronym is a brilliant way to remember the signs. Has their face dropped on one side? Can they lift both arms? Is their speech slurred? If you see any of these, it's time to call for help. Fast.
And once in the hospital, the entire toolkit we've been talking about is vital. A CT scan can quickly show if there's a bleed or a clot. A PET scan can reveal which areas of the brain aren't getting enough blood. And, crucially for recovery, an fMRI can be used to map how the brain starts to rewire itself after damage, helping people regain precious abilities like speech or movement.
Okay, deep breath. Let's pull all of this together. Here is your ultimate revision guide with everything you need for your IGCSE psychology exams, all in one neat package. This table is your new best friend for revision. It gives you a really simple side-by-side comparison. In short, CT shows structure, the what. PET and fMRI show activity, the doing. But fMRI is the top choice for modern research because it's safer, faster, and gives us a much clearer, real-time picture of the brain at work.
And here you have it, the whole story in one place. We started with that big concept of localization. We looked at the scanning tools that let us investigate it. We saw how those tools helped us understand the difference between episodic and semantic memory, all brought to life by Tulving's key study. It all connects.
And I'll leave you with this final thought. This technology is getting more powerful by the day. As we get better and better at mapping thoughts and memories, what kind of tricky ethical questions are we going to face? And how do we make sure that this incredible power is always used wisely?